Welcome to another exciting day here at Spain Park Advanced Level Chemistry. This is just a quick fill-in of the demonstrations on why or how polarity affects solubility. Okay? And the key here is that polar molecules, I don't want to erase that. Polar molecules dissolve in water and other polar solvents where non-polar molecules are soluble in non-polar, such as gasoline or mineral spirits, paint thinner. Okay? This is right here. This is on your old notes, not the packet that I gave to you. This is.
Where?
I skipped over this one though. Okay? All right. Well, the whole thing is that like dissolves like. Okay? So let's kind of look at this. Okay? We already know it. I mean, it's just this. Like dissolves like. Polar dissolves polar. Non-polar dissolves non-polar. This is a basic styrofoam cup. Okay? Does anybody know what styrofoam is made of though? Okay, we're going to do just a little bit of random organic chemistry. A little bit about recycling. Okay? So, we have this basic molecule. This was number 15 on our Lewis dot, or number 12 on our Lewis dot structure worksheet. Okay? This is known as a monomer, which is a single merge. It's the starting material for a polymer. This is known as ethene, which the old school name of it is vinyl. It's 2 carbons, C2H4. But if I bring another ethene, just like it, okay, we can, with the right chemicals and the right temperature and pressure, we can cause the double bond to break. Now, which bond, the sigma or the pi bond, is going to break here? The pi bond, remember the pi bond is always the weaker bond. There's less overlap, okay? The second and third bonds of a double bond are always pi. The first bond is always a sigma type bond. So this, the pi bond is going to break, but that's going to let each carbon form 2 more bonds on each side, form a bond on each side. So then you can bring in a whole bunch more of these, and you can end up getting a chain that just goes on and on and on and on. Hydrogen, 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 hydrogen. So we would call this whole thing polyethylene. Now, number 2 recycle is HDPE. If you look on the bottom, you see a little triangle on some plastic thing, like that antifreeze container has a triangle with a 2 in it. That stands for high density polyethylene. That just means you have that density, you have low density polyethylene as well. And that just depends on how many carbon chains they have and how they kind of link them together. It's like spaghetti noodles. You can kind of twist them all together and make it firmer. Okay? So that's polyethylene. Now, if I make one small change to it, I put a chlorine right here and a chlorine right here, that's going to make every other carbon a chlorine. Now this name is vinyl chloride, using the old school name. So what would this be called? Polyvinyl chloride. Now, you've heard of this, but you may have heard of it with the abbreviation PVC. The white pipes, the PVC pipes, are polyvinyl chloride. The chlorine adds extra strength and extra hardness to the plastic, and so they can make a PVC pipe out of it. It's polyvinyl chloride. It's just this carbon in this long hydrocarbon chain, but every other carbon has a chlorine. Let's make one other modification. A benzene ring looks like this, and it's C6H6. Okay? So this represents C6H6, just a lot easier to draw it like this. So if I replace the chlorines with the benzene ring, every other one, now I have styrene. So what do you think this name, the whole thing, the polymer is going to be called? Polystyrene. So this is the starting material. So now when they go and they make the cups, all they do is blow air through the polystyrene, and they make it real porous with air pockets, and so it's called polystyrene. It's called styrofoam, okay, but it's really just polystyrene. If you've ever been to a cafeteria where they give you a real tray instead of the styrofoam trays, you know, I think they used to in the cafeterias here. You ever went to Piccadilly cafeteria, any of those at the mall? They give you a real tray. That's actually polystyrene. It just doesn't have the air blown through it. So it's the exact same stuff as this, but it just doesn't have the air. Okay? So saying all of that, you can see that all of these compounds are hydrocarbons. What do we know about the polarity of all hydrocarbons? I heard a mumble. You got a 50-50 chance. Polar or non-polar?
Polar. Non-polar.
Don't play the lottery. Non-polar. Okay? Are there any fluorine, chlorines, nitrogens, or oxygens in it? No, and it's all symmetrical. No lone pair on the central atom. Okay? Hydrocarbons as a whole are non-polar. Okay? So this is a non-polar substance. So if I go and I put in, well, first off, let's just prove that water is polar. Okay? So I have a stream of water. Back in the day when they were first, determining charge, they used a rubber rod and cat fur to determine whether or not one thing's positive, one thing's negative. So I'm getting static electricity. But if I take this next to the water, just like an avatar, I am a water bender. Okay, and if you need to get out of your seat to be able to see this, you can come and get out of your seat to kind of see. But the water is actually bending towards the rubber rod. Okay, this because this has a charge on it, and water's polar, so the polarity, I don't know if this is positive or negative. I think it's negative, so the positive side of the water is being attracted to this negative rod.
Pretty sure you're just using strings.
I'm telling you, it looks like magic, but it's just science.
No,
It's just science, okay? Bending the water.
You're a water bender.
I am a water bender. I need to make my own movie. Okay, so water is very polar. So if I take polar water, I think I'm glad I missed that. If I take polar water and I put it into my non-polar cup, styrofoam cup, it's perfect. Okay, I can put my hot chocolate, I can put my coffee in there, or I can put my ice cold Diet Mountain Dews in here. Okay, but the big question is it keeps hot things hot and it keeps cold things cold. How does it know? How does it know? How does that work?
It doesn't.
It does. It keeps hot things hot and cold things cold. We know it works. What does that mean, insulator?
Keeps the temperature in.
Keeps the temperature. Temperature isn't a thing.
It like keeps in whatever energy from whatever. Yeah.
Okay. It doesn't allow for heat transfer. Okay, that's what the words you were looking for. Okay, so if it's hot on the inside, the heat can't get through. It's an insulator. The trapped air is a great insulator. Okay, you have insulated windows. You don't have pink stuff in between the windows. You have trapped air. You have a gap with a trapped air in between that's a low pressure, but it doesn't allow for as much of the heat to transfer through. So anything that I put in here that is water-based, polar, it's going to be good. But if I went and had my fingers done and I had some gel put on them, okay, I don't know, have any of y'all ever seen Angela Johnson, Bon Qui Qui, you know, going to the nail salon, you know, you got boyfriend, anyway.
Oh.
You know.
TikTok?
Yeah, well, it's probably on TikTok, but I mean, it's on, I saw it on YouTube, okay? But anyway, she's going in to get her nails done, and the lady's trying to upsell her, you know, so you need gel. But my wife actually had gel on her fingers, and when she went to get it taken off, apparently it's really hard to get off if you have a gel on there. So you might want to soak your fingers in some fingernail polish remover. And what's the main ingredient, ladies, in fingernail polish remover? Acetone. So here's some acetone. So I'm just going to put some in this styrofoam cup. Now let me just tell you, acetone's formula this is acetone's formula. Now yes, it does have an oxygen in it, but it's right in the middle here. This is mainly a hydrocarbon. It's pretty much nonpolar. Okay? So when I go and I take and I put nonpolar acetone into the nonpolar styrofoam cup, we end up having an issue because like dissolves like dissolves like, and eventually the whole bottom kind of gives way. Okay?
It's a bottomless cup.
And how it is a bottomless cup, and it's not melting because it's actually quite cold. It's dissolving. Just like the problem with the Wizard of Oz is when you throw water on the Wicked Witch, she's yelling, I'm melting, but she's really dissolving. Okay, she wasn't melting. Like dissolves like. So, okay, now I'm going to give you a little bit of information that I'm going to deny I ever shared with you. But have any of y'all ever heard of a napalm bomb? Okay, they used it in Vietnam. So if I want to go to my local neighborhood riot and I want to bring a Molotov cocktail, okay? A Molotov cocktail is a wine bottle that you fill with gasoline. Then you put a rag in the top of it, and the rag is soaked in gasoline as well. You light it, and you throw it against the wall of the building that you want to get a TV out of. Okay? And so, okay?
Yeah.
Do what? Yeah. Okay? So, you throw it against it, but the gasoline is just going to run down to the bottom, and it's going to burn down at the bottom. So some genius said, hey, listen, we can dissolve styrofoam into gasoline. Then the gasoline becomes more of a gel. So now when I make my Molotov cocktail and I throw it against the wall, now it's going to stick to wherever it hits. It's not just going to run down to the bottom. So it just makes it a sticky, flammable substance. And so that's what napalm is. Now, do not attempt this at home. I've been telling this for a long time. And one of the students from Spain Park, in one of the very first years, he went home and made some napalm in his garage, okay? Dissolved some styrofoam cups into some gasoline from his lawnmower, okay? And he threw it, lit it, and threw it against a tree next to his garage. He almost burned the garage down. And I heard about this from his little brother that told the story when I was telling the same thing. Oh yeah, my brother did that, you know, so don't do that at home. Okay? No, that's not smart. Okay?
It sounds pretty cool.
Do it somewhere where you're not going to burn anything down. You're not going to start a forest fire. You're not going to start a wildfire on the field. Okay? You're not going to catch yourself on fire. Okay? Do not attempt this at home. Okay? Now, I bring that up too because in Baton Rouge, there's Dow Chemical Company has this big, huge plant there, and part of that is they have a big incinerator which they can burn things to such a high degree, high temperature, that it actually breaks it down into the elements and makes toxic things not toxic, okay, because it's just breaking it into the elements. Well, they made a contract with the government to burn some of the old napalm bombs from the Vietnam War, and so everybody in Baton Rouge started rising up. We don't want the napalm coming through the streets, you know, it's dangerous, it's explosive, da 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 da. But the reality is, we have gasoline tanker trucks run on the roads all the time, filling up all the different gas stations when they have those underground tanks. If a gasoline tanker crashes and it ruptures, the gasoline's going to run everywhere, get in the ground, go into the water. It's going to be a major cleanup. But if a napalm bomb tanker, it's just going to be a pile of gel just in one spot that's going to be much easier to clean up. They're both very flammable. It's not going to run off everywhere. So the reality is the napalm was safer, but people were all freaking out because they didn't know. And so a lot of times we get a little bit stressed on things because we're not properly educated, which is why I always try and get you to be scientifically literate. Know about radioactivity. Now you know about napalm. Okay?
I remember.
So, one other example of this. Okay? I'm going to take some water. Well, before I do that, so I'm going to take some water. Obviously, water looks like this, and we just decided, is water polar or non-polar?
Polar.
Very polar. Water is one of the most polar substances. Okay? I'm going to try to dissolve some iodine into it, I2. Okay? What's the polarity of I2? Non-polar. But then I can put it into some hexane. Hexane. Okay? What do we think on the polarity of that one? Non-polar. It's a hydrocarbon. There's no fluorine, chlorine, oxygen, or nitrogen. Non-polar. Hydrocarbons tend to be non-polar. Okay? So what do we expect in terms of solubility? If I just take some water, and we run out of little ones. We don't have any hot water today for some reason. Okay, so I'm just going to take a little bit of water. Iodine is a solid. Just take a little bit of iodine.
What do they use iodine
What do they use iodine? Iodine's used in medicine a lot, like a tincture of iodine. They use it as an antibiotic, beta iodine. Iodine's used for a lot of different things, but we're going to use it. Wow. That's interesting. It's not supposed to do that.
You broke science.
Shit.
You should research it.
Well, there must have been something in this test tube already. Yeah, that or this is special water. Is right.
Yeah,
Okay, let's try this again. Take some iodine. Just a little bit. Put it into here. That's better. Okay, and then when I shake it up, basically now, you can see that nothing's happening. You got the little bit sitting down here at the bottom. There's no color change. Nothing's happening just as we predict. Okay? Now, if I take some hexane, put it in here, and now I go and I put some iodine into it. Now, you can see that there's a color change. And iodine in its natural state is purple. So you can kind of see it's going and dissolving. Right now it's kind of a light purple, which is a pink, fuchsia, magenta kind of color. But as more and more of it dissolves, okay, it's going to get a darker and darker purple. Now, if I take these two and I mix them, I just put a little bit of water. I don't think any of this is on Chromebooks. I don't think any of y'all need to have your Chromebooks open. doing stuff, okay? Okay, because I know that you're not doing stuff. So we put this into here. But because the water is polar and the hexane is nonpolar, they don't mix. And so they're going to quickly separate. Now you can see it's really starting to get more purple now up here, and then you get this layer here. Okay, so they don't want to mix. But in life, we always want to find someone that can be kind of a peacekeeper. Okay? Someone that can kind of make two people kind of be able to come together and hang out. So if I take some ethanol, some ethyl alcohol, it looks like this. Now, ethanol has this hydrocarbon portion, which is pretty much nonpolar, but it's also got this oxygen, hydrogen out here that's polar. So we would say it's a polar molecule, but we have all of this part right here that's nonpolar, and this part that's polar. Now again, if I ask the question, is this a polar or nonpolar molecule, you'd say it's polar. But the reality is it's only part of it is polar. This is a nonpolar part. So this nonpolar part can hang out with the nonpolar. The polar part can hang out with the polar. So we call that, this right here is what we call an emulsion. Two liquids that aren't soluble in one another. It's an emulsion, like Italian salad dressing. You got to shake it up right before you pour it because the oil and the vinegar don't mix. So if I take some ethanol and I mix it in here, and I shake it, now I'm still going to end up getting two layers. It's not going to be complete, but notice now that down here in this water layer, there's more of a yellowish and it can go even more brown. The alcohol is allowing some of the iodine to dissolve into the water. And it's actually allowing some of the water, notice it's less purpley up here now because some of the water and alcohol are dissolved in this as well. So we've got a nice purple and gold, go Tigers, an emulsion here, but the alcohol is acting like an emulsifying agent. It's linking those two together. In Italian salad dressing, they add egg whites, and you get creamy Italian that doesn't separate. You've added an emulsifying agent. Mayonnaise, you've added an emulsifying agent, and so it doesn't separate. The most important emulsifying agent is that of soap, which I'm hoping y'all are all familiar with. Find the picture, chapter 13. So if we look at this, you know that if you go and take a shower and you don't use shampoo, your hair is still going to be oily. It's kind of unfortunate that our scalp just naturally produces oil, but it does. And so you have these oil droplets that it's non-polar, that it's not going to mix with polar water. So you need an emulsifying agent. Now all soaps, okay, are going to have this long hydrogen. The black spheres are carbons, the whites are hydrogen, and these reds are oxygens over here. So we have a long non-polar portion and then a polar portion over here on the end. So when you have an oil drop, and you use the shampoo comes in and attaches to the oil drop, but the polar part doesn't. It's hydro. What does hydrophobic mean?
It doesn't like water.
Doesn't like water. Hydrophilic is the lover of water. Okay? So the polar end is the hydrophilic end, and so the water can then come in and attach to this part, and it links the oil and the water together and allows it to go down the drain. And your hair comes out clean. And so all soaps are these long hydrocarbons. They're emulsifying agents. They're a combination of nonpolar and polar. The nonpolar part dissolves the nonpolar oil. the polar part dissolves in the water, links them together, pulls them into solution. Okay? Now, another little tidbit. This is totally 100% oh my. In ancient Egypt times, they had things called sapons. S-A-P-O-N-S, sapons. And so they were naturally sudsing things, and they found those and they used those to clean their clothes down at the river. Well, nowadays, a soap, the only difference between soap and detergent is soap is still made from natural materials. So does anybody know what soap used to be made out of? Made from? No? What? No? Animal fat. Okay? Animal, not poop, animal fat. Pig fat is called lard. Cow and sheep fat is called tallow. And so they would take that and then they would treat it with lye, L-Y-E, which is the commercial name for sodium hydroxide. And they call it a saponification reaction because it turns the fat into a sapon. It turns the fat into a sudsing thing that acts as a soap. So it was really, really harsh, so you couldn't use soap every day because that sodium hydroxide is very corrosive. And so you could only take a bath with soap like once a week, once every 10 days, which is why Europe came up with colognes, because you had to kind of cover the body odor because you couldn't use soap all the time because it was too harsh. Okay? I actually went to a fancy hotel a long time ago, and being the nerd that I am, they had this fancy soap in a box. And when I actually looked at the box, I looked at the ingredients. Oh, I wonder what this soap's made out of. And if it clears up enough.
Yeah, you gotta turn off the
If I turn off the lights, it's not gonna work. Because it needs the light to see. Anyway, I'll just read it to you. Make it get real big. Not that big of a deal. Right there it says sodium tallowate is the main ingredient. Now, that's just a general name, but this was made actually from cow fat. This soap was. Okay, it could have been sheep fat. Okay? So, they treat it with sodium hydroxide, and then you end up getting that. Then they add other things to it as moisturizers to help soften the blow some, as make it not as harsh as old soaps used to be. Okay? Now detergents are generally made, modern soaps are made from soybean oil. So they used to have tone with cocoa butter made from coconut oil, you know, and the different things on sources of the oil. But they're all long hydrocarbon chains, non-polar ends with a polar tail, and they're emulsifying agents. All right, last thing on this. What is dry cleaning? What's the difference between doing your laundry versus dry cleaning?
It makes it dry to your clothes.
Does dry cleaning treat it dry?
Yes.
Those of you that have got stuff back from the dry cleaners, does it feel dry?
Yes.
It's usually steam.
Does it smell dry? Does it smell? It's not steam because that would still be water.
Yet.
Hey, we don't need that kind of crap, okay? I'm really tired of that, okay? That's very junior high. You need to grow up, okay? Now, dry cleaners do not use water, but it's also not dry. They don't I used to think they used a powder of some kind to clean them, but they don't. They use a non-polar solvent because something about your clothes, the polar water is going to kind of mess it up. So you got to have a non-polar solvent in order to be able to get your clothes clean. That's why when it comes in the plastic and you put it in your closet, you sometimes can smell that solvent. Because it needs to evaporate quickly so your clothes will dry. But they just use a non-polar solvent in the dry cleaning because they try not to get the color that something in your clothes is going to react to the water that you don't want to put it into. The same thing with stain removers. When you want to have a stain remover, say you get a mustard stain, you need to find something that has a similar chemical property to mustard to get the stain out. But the problem is does it take the color of the clothes out as well? And so sometimes you get the stain out, but then you have a white splotch or whatever. And bleach, on the other hand, Bleach only makes the dirt white. It doesn't get the dirt out. It just covers it up and makes it look white. And so bleach doesn't do anything to clean the clothes. It just helps them look better. All right, so let's look at this worksheet then. Well, before I do that, let me give you one more piece of resource material. This is all of our different types of substances in the bonds too. That might be 3. I'm guessing that's cool. My fingers are too dry. So this shows all the different types of substances that we've talked about, the bonding. Normally we talked about them being 4 different types. Ionic, metallic, covalent, network, and covalent molecular. But covalent molecular has been broken down into polar and nonpolar. And even polar then has to be broken down to, does it have dipole-dipole, or does it have dipole-dipole and hydrogen bonds? So we always have to check to see what force is holding it together. This whole packet that we just did is all about covalent molecular, polar versus nonpolar. Hydrogen bonds, do have hydrogen bonds or not? So when we look at this, let's go through quickly. What time are we out of here?
We got 5 minutes.
At 1?
Well, for speed.
For some reason I was thinking 10. Okay, so the first thing is, this is pretty easy. Obviously, this is a solid, this is a liquid, this is a gas. Okay? Solid, liquid, gas. Okay? So which one has the stronger attractive forces? Solid. Okay? That's pretty obvious too. So now we look here and we can see a covalent bond and ionic bond are 800 and 400. Okay? And then now our intermolecular forces. This is the key. We have to see that these are significantly smaller. Now we definitely need to stress that these are the bonds between the molecules. Intermolecular forces, between molecules. This is a covalent bond, covalent bond, covalent bond, covalent bond. This is your London dispersion force that what holds molecule to molecule. So, intermolecular forces are non-covalent interactions between molecules. Which group consists only of intermolecular forces? A or B? B. Okay? Group A is what we call intramolecular forces, within the molecule. Okay? So obviously, I mean, this one's real tough here. How do we determine which bonds are the strongest?
Look on the right side of the table.
Well, the biggest number, right? So 800, an ionic bond, then a covalent bond, 400, then a hydrogen bond, then dipole-dipole, then London forces. It's just the order of the number. Which are stronger? Group A or Group B? Group A, because you have a higher boiling point. That's how you measure the bond strength. How much energy does it take to break it apart? Okay? When you're boiling water, which bonds do you think you're breaking? If I have a bunch of water, am I going to break the bond between the oxygen and the hydrogen? Am I going to break the bond between the water molecules? Between those hydrogen bonds. Well, it's actually, water's going to have all 3. If you have hydrogen bonds, you have all 3 types. Okay? But hydrogen bonds are the most significant. They're the strongest of the 3. Okay? So when your water boils, what's in the bubble? Water. Water's in the bubble. Is steam. Because steam is what's coming off the top. So you're not breaking this bond to make it hydrogen and oxygen. This bond's way stronger than the bond holding the water molecules. The bubble is just the water molecules have had enough energy to break apart and form the bubble. Okay? So next time you're making spaghetti noodles and you see the water boiling, just realize, ooh, that's water vapor inside all of those bubbles. Okay? So, when you're boiling water, which bonds? The covalent bonds or the intermolecular forces? Intermolecular forces. Okay. So now here's your melting points. Now you have to label these as polar or non-polar.
Did we say Q6 group D? I'll make group A.
Yep.
So which ones of these are polar and non-polar? Is CH4 polar or non-polar? Non. What about C2H6?
Non-polar.
Non-polar, okay, because they're hydrocarbons, they're always non-polar. What about these three?
Polar.
All polar, they got phone call in them, all of them, okay? They're all polar. Which one is going to have the strongest attraction forces between the molecules? H2O. How do you know that just like that? Highest boiling point. Highest boiling point is always going to mean the strongest attractive force. Okay, so assign each molecule as polar, we just did that. What does this mean? The more polar the molecule, what does that mean about the higher or lower?
Higher.
The higher, because it's going to have stronger dipole-dipole attractions. So if you want to add that in, it's going to have stronger dipole-dipole attractions. And then the more polar the molecule, the stronger its intermolecular forces. These two go together. The stronger the intermolecular forces, the higher the boiling point. They're directly proportional to one another. Stronger forces, higher boiling point. It takes more energy to break them apart. So which do you predict to have a higher boiling point, CO or CO2? Why CO?
Because it has a higher boiling point.
But why? You're predicting it. Why?
It's polar.
Because it's polar. Okay? Yes, this one's a little bit heavier. It's going to have a little bit stronger London forces, but this is polar, so it's got dipole-dipole as well. Now, we had to change the numbers on here to this one. So where does 25 fit? So this one is going to be, I know, but we're talking here, assigning a solid, liquid, or a gas. Gas, gas, liquid, because 25 is going to be right in between these two numbers. Okay, so it's higher than its melting point. So 25, it melted negative 7.2, so it's melted at 25, but it hasn't boiled yet. And then here, the 113, it hadn't even melted yet, and so iodine is going to be a solid all the way through. Okay? So which must have the highest IMFs? Iodine. Highest melting and boiling points. Now, why would it have the highest melting and boiling points? What's the only, well, first off, are all of these polar or non-polar? Non-polar, right? So what's the only type of attractive force? I know, but which one of the three? London, LDFs. What do London forces vary with? How do they get stronger? The bigger the mass. It's really the size of the electron cloud, but that's the same as the mass. Bigger mass generally means bigger electron cloud. Okay? So they're all non-polar. There is a relationship, no relationship between polarity here because they're all non-polar. But what is the relationship between molecular weight and boiling point then? What did we say? What's the relationship? The higher the molecular weight, the higher the boiling point, and again, why? What's stronger? London dispersion forces. Okay? And that's the only type of attraction between these is LDS because they're all non-polar. So that's kind of what I have on the board here. LDFs are the only type of IMF between non-polar molecules. But all molecules have LDFs. Okay? All molecules have them. So then we got to just kind of keep looking then. I wish I'm having a race. Okay. Higher boiling points, higher molecular weight because stronger London forces. So now complete the following. As the molar mass of a compound increases, the strength of its intermolecular forces Increases, and specifically what force? LDF. So you might want to just put LDFs under here versus just intermolecular forces. Because molecular mass only affects LDFs. So now here again, these are all noble gases, so they're all basically, there's monatomic, they're all nonpolar. So this shows again, and these are all hydrocarbons that are nonpolar. You can see as the molar mass increases, so does the boiling point. Does the statement you completed in the previous question agree with the data above? Yes. Greater molar mass, higher boiling point. Now this is really good stuff right here. To be honest with you, this is AP level stuff right here, talking about this. Notice the trend here. Each molecule is getting bigger and bigger and bigger as you're going down the family. These are all getting greater and greater molar mass, bigger and bigger electron clouds. So as a result, the boiling point's increasing. Same general trend here. What's unique about water that why it doesn't come down here like this other one?
It's polar.
It's polar and it has what? Well, what's unique? What's the special bond with water? It can form hydrogen bonds. Okay, that gives it extra strength, and because of that, water has these highly unusual characteristics. Okay, so this is because of hydrogen bonding. Here, these are all pretty much non-polar, so they just have the London forces, but this has the hydrogen bonds, which are much, much stronger. So, in which substance are there stronger intermolecular forces? CnH4, CH4? SNH4, right? Okay? Because what type of attractive force is it? What type of attractive force is it between all these molecules?
Intermittent.
Which type of intermolecular force is it for nonpolar molecules? London forces. Increases with molecular mass. Okay? How can you tell based on the graph? Highest boiling point. Explain based on what you have learned so far why your choice should have stronger intermolecular forces. It's going to have greater molar mass, stronger London forces. Okay? Stronger London forces. Greatest molar mass. Now the bottom line of the graph shows one trend and the top line shows a very different. Which are stronger, H2S or H2O? H2O, higher boiling point. Why? You just said it.
Molar mass.
No.
Higher LDF.
No, because H2S is going to be a greater molar mass, it's going to have stronger LDFs.
Oh, so polarity.
Polarity, but what specifically, what does water have that this doesn't have?
Hydrogen.
The ability to form hydrogen bonds. And then that point is stressed again on the next graph. When we look at that graph, so now we have 3 periods that they're going across. What do all 3 of these have that these other ones don't have? Hydrogen bonds. So I would circle all these on my paper and say all have hydrogen bonds. That's why they're unique. That's an exceptionally strong intermolecular force. Almost all the time on questions like this, the answer is going to be hydrogen bonds. Why does one thing have a higher boiling point than the other? One is hydrogen bonds, the other one doesn't. There's going to be stronger intermolecular forces than expected. Hydrogen bonds right here. Okay? These 3 deviate. Besides H, which other elements are in these? F, O, and N. Foam. Compounds containing a hydrogen bonded to the elements. Fluorine, oxygen, nitrogen. Okay? But hydrogen bonds are not the same as covalent bonds. We'll talk about that finish on Tuesday. Okay, go ahead and scan this in. There's a place to scan in your packet. Just do that over the weekend.
Are you close?